Hello everyone. So welcome to my next video on SystemVerilog for verification. So here we will discuss another important construct, that is the program block. So in this video we will understand what it is, how it differs from modules, why it is used in verification environments, and we will explore its simulation behavior. So in Verilog, both the design and the test bench both are written using the module construct. So using the module construct, it is very simple, but it can actually lead to race conditions. And that is because both the design and the test bench both execute in the same simulation region, that is the active region. So let's understand this with an example. So we have a module duty, and initially it is setting value of x to 0, and inside the initial block we are setting value of x to 1 using non-blocking assignment. And at the same time we have another module, test bench module, which is trying to read the value of x and display it. But because both the initial blocks, both of them execute in parallel and in the same region, so the test bench might read the old value of x, which is 0, because this is the non-blocking assignment, and this display would occur in the active region. So this would execute before the non-blocking assignment. So as a result, the output would be x equals to 0. Even though we have assigned x, we have assigned value 1 to x. So this behavior is very unsafe in verification, and that is exactly why SystemVerilog introduced the program block. So in SystemVerilog, we solve this race condition problem by using the program block for test benches. So here, unlike modules, a program block runs in a spatial simulation region which executes after the design logic has been executed. And it clearly separates the test bench from the duty, and it ensures correct order of execution between test bench and design modules. So here we have the same example from earlier, but this time we are using a program instead of a module for a test bench. Now when the design assigns x equals to 1 using non-blocking assignment, so this change is guaranteed to be complete before the test bench reads and displays the value of x. So that's why the output clearly shows x equals to 1. So this sequencing eliminates race conditions, and it ensures that the design is evaluated first, followed by the test bench stimulus and checks. So here are some of the key features of the program block in SystemVerilog. So firstly, it provides an entry point to start executing the test bench. It avoids race conditions by ensuring that test bench code executes after the RTL logic during simulation. Program block does not allow always blocks. Only initial blocks and tasks or functions are allowed. So like a module, it can also have ports. You can explicitly end the execution of a program using $exit system task. A program block can be instantiated inside a module, but the reverse is not allowed. Means you cannot instantiate a module or another program block inside a program. Finally, a program can access variables from its parent module. So another feature of the program block is that its statements are executed in the reactive region of the simulation cycle. And this reactive region comes after all RTL related activities in the design are completed. And it also ensures that test bench code does not interfere with the RTL logic. So if you remember, the event region flow during a simulation follows this sequence. First is active region, then inactive, then we have a non-blocking assignment region, then observed, and then reactive. So reactive region is where the program blocks execute, and it ensures that the test bench runs after the design updates, because design update already happened in this active, inactive, and NBA region. So this reactive region is safe for the verification task. So SystemVerilog divides this reactive region into three sub-regions: reactive, re-inactive, and re-NBA region, to manage all the test bench execution. So first is reactive reason. It executes initial and final blocks written inside the program block. Then comes the inactive reason. It holds new events which are scheduled during the reactive phase. And finally, we have a re-NBA reason. It handles non-blocking assignments which are scheduled inside the program blocks. So these assignments update after all reactive and inactive reasons finish. So this example shows how different reactive reasons behave during simulation. In this example, we have defined a program block named test, and inside this program, we are declaring a 4-bit logic variable val. Inside the initial block, firstly, we have defined value of val as 4, and it happens in the reactive reason. Next is hash 0, so it represents a 0 time delay, and it moves execution to the inactive reason. Then we have val equals to val plus 1 using non-blocking assignment, so it gets scheduled into the NBA reason. Then we have a $display statement which would execute in the reactive reason. And then after a delay of 1 timestamp, again we have a $display statement which also would execute in the reactive reason. So if we understand the execution at timestamp 0, first val equals to 4 would be executed in the reactive reason. Then in the reactive reason, this $display statement would be executed and it would display the value as 4. You can see the output val equals to 4 at timestamp 0. Then the inactive reason comes and this statement would execute, and in the NBA reason, this value of val would be updated to 5. Then in the next timestamp, this $display statement would execute in the reactive reason, and now it would display the updated value, that is 5 at timestamp 1. So here we have another example where we are writing a simple test bench using a program block to verify an ALU design. So in this example, I have not added the RTL code for the ALU. On the left hand side, I have defined a top module which declares signals for operands A and B. OP is the operation code, and we have output result. So the ALU module is instantiated and connected to these signals, and we also instantiate the program block named test bench. On the right hand side, we are defining the program block. Inside the initial block of the program, we are applying values, we are applying stimulus. So we are applying values to the operands A and B and to the OP code. So OP code 00 means addition, OP code 01 means subtraction, and OP code 10 means ending. So each of these operations is happening after a delay of 10 time units. So this example shows how program blocks cleanly separate the test bench logic from the design. Because this program block would execute in the reactive reason and design has already been settled in the active reason. So this would ensure the race-free execution, and it also ensures the correct order of execution between test benches and design modules. This is an assignment based on program block. So you have to write a design description for 4-bit counter that counts up or down based on a control signal. And you have to write a complete test bench for this using program block to drive stimulus. Make sure you do not write any always block inside the program, and the clock generation must be done in a separate modules. And then you have to display outputs using $display statement. If you have any questions or queries, you can send me an email on this mentioned email ID, or you can connect me via LinkedIn. Thank you.